Okay, so good morning. Welcome to Computational Complexity. Let's share the screen. I want to go to okay, so today, instead of the board, I found out I've got too much material to present it on the board, and I do want to cover it all today because I only want to spend 1 week on this topic. So instead, I have notes largely prepared, and I'll add some annotations as we go along. You can either take your own notes if you want to, but you might not be able to keep up with everything because I'm going to be going through notes that are already written, so it won't be as slow as it usually is. But the notes that I'm looking at, these handwritten notes on the screen, are going to be available on the course web page. Okay, so today we're going to look at revising our computational model to incorporate a new form of computation, which is still a realistic form of computation, but the advantage of considering it is it allows us access to some algorithms that rely on this feature, and this feature is randomness. So being able to, the computer essentially being able to toss a coin and pick a random, make a random choice with some probability. And as we shall see, this is very useful. And what it allows us to do is, whereas we've got this notion of this idealized notion of efficient computation as computation that runs in time that's only polynomial, that time that grows only polynomially in the size of the input, we can now, so we've got the deterministic polynomial time as a realistic model of computation, but actually if we add randomness, then potentially it allows us to expand on the class of algorithms we have that are efficient, if we take efficient to mean run in time that's polynomial in the size of the input. So we're going to introduce you today to this new complexity class, BPP, bounded probabilistic in polynomial time. And this class is, in some sense, really the better model of efficient computation, because they're efficient in the sense that the algorithms in this class are efficient in the sense that they run in polynomial time, but they're a little bit more, we're being a little bit more inclusive because we're allowing ourselves to use, and this is a realistic feature because one can actually do this in real computation, we're allowing ourselves to use essentially the throw of the dice to help the computation process. So let's start by looking at, so I'm going to actually do this one, writing down, looking at a little, a very simple probabilistic Turing machine. Hello. And what this Turing machine does is it's going to start in state start, as it always does. And we're just going to have two transitions. So in state start, then I'm going to use this underscore as a wildcard. So no matter what is on the, no matter what, we've got a single head, but no matter what symbol it's looking at, one possible transition is to stay in state start. We'll keep, I again use the wildcard, it just means keep the same symbol on the tape and keep the head position where it was. So the 0 is the head position. Movement. And we're going to make it non-deterministic. So we'll give it two possible transitions. So also in state start, no matter what symbol it's looking at, then we'll also allow it to go to accept, which is of course a halting state with the same symbol, and also keep the head position there. So we've got two possible transitions. So it looks just like a non-deterministic Turing machine. In state start, it's got two things it can do. It can either stay in state start, in which case it again has two things it can do. And if it stays in state start a third time, then again, it's got two things it can do, and it'll keep on ticking along in state start until the other non-deterministic choice is to go into state accept. And if it goes into state accept, it halts. So it looks like a non-deterministic Turing machine, but it's probabilistic because instead of saying, we don't know which path is going to be taken, that's for some oracle to decide for us who's trying to find the right answer, which is kind of the idea with non-deterministic Turing machines. And that's not a realistic model of computation because one doesn't know where one can find the oracle that will point us to the right answer. And that one can't do that in computation. One can't tap into God, so to speak. But what one can do in computation is toss a coin, make a fair random choice between two possibilities. And so the probabilistic Turing machine just has a different interpretation from the non-deterministic Turing machine. We're in state start, and in that configuration, it'll pick with probability half to stay in state start and with probability half to move to state accept. So the probabilistic transition to Turing machine switches between, chooses between the two possibilities. Two possible transitions. By tossing a fair coin. So this Turing machine has very simple behavior. All it can ever do is accept, or it might potentially, if it keeps on, if we say this is heads to go to start and tails to go to state accept, if it keeps on tossing heads, then it'll just loop forever. Of course, the probability of that happening is 0 in the long run. Eventually, with probability 1, we're going to go at some point to state accept. So we see that this Turing machine already illustrates, it's very simple, but it illustrates a few of the concepts involved with probabilistic computation. So the worst case runtime of this Turing machine is infinite. Right? Because the worst possible path it can take is just to stay in the start state and tick along forever. But at each point in time, with probability a half, it'll go to accept. So the probability it halts after one step of computation is a half. The probability it will have halted after 2 steps of computation is 3/4. The probability it will have halted after 3 steps of computation is 7/8, and so on. And so the probability it will eventually halt is 1. So the worst case runtime is infinity, but the TM halts with probability 1. And when that happens, it makes sense to ask, what is the expected runtime of the Turing machine? What is the average runtime of the Turing machine? We've got probabilistic choices that we're randomly choosing the path of computation. For each path that terminates, we have the runtime for that path. And then we've got all the possible paths over all the random choices that have been made. So what's the average or the expected runtime of the Turing machine? So does anyone know in here what the expected runtime of this Turing machine is?
I think it's 2.
Yeah, who agrees with that? So yeah, that's right. So the important statistic we have associated with this is the expected runtime. And why is it 2? Can anyone reason that?
So it's a geometric distribution.
Yeah, so it's the sum. So if we sum over all the possible numbers of steps, it must take at least one step. The probability that so we want to sum n times, so that's the number of steps times the probability that it will terminate at exactly that number of steps, and the probability it will terminate at exactly n steps is 1 over 2 to the n. So we're considering the sum of from n equals 1 to infinity of n over 2 to the n, and that's a famous identity, which it's fun to verify for yourself. I'm not going to do it now. But, sorry, it's not 1, that's 2. If that was 1 over 2 to the n, it would be 1. But when it's n over 2 to the n, that's equal to 2. Okay. So that was an example probabilistic Turing machine. Sorry. So probabilistic Turing machine, what do we need to specify it? Well, in general, it very much looks like a non-deterministic Turing machine. So it's exactly the same data for a non-deterministic Turing machine. We give the TAFE alphabet, a finite set of states, and once again we have a transition relation. And so it's exactly the same data. I know this is too fast to take notes, but for those of you who weren't here at the beginning, the reason I'm presenting like this is because I've got too much to take notes. So you can take the appropriate notes, but these notes that I'm showing you will be available on the course webpage. So it's exactly the same data we use to specify a non-deterministic Turing machine. However, the probabilistic Turing machine, the only difference is the way that we interpret the data for the Turing machine. So we have a different execution model for the Turing machine. Rather than relying on some oracle to choose the path for us, we're going to toss coins to decide on the path. And the important thing is that this is a realistic model of computation, because one can, in various ways in a computer, tap into sources of randomness, either using random number generators, or typically computers also make use of a bit of randomness from the environment in some way. So we need to say what the execution model is. And the execution model I'm going to have is that a probabilistic Turing machine always starts in the start configuration. And it proceeds as follows, that from any configuration, if you're in a configuration, we've got the transition relation of the Turing machine. The transition relation is a finite relation. And from any configuration, there may be no possible configurations to which it can move to in one step, in which case that's a terminating configuration. There may be one, in which case it deterministically goes to that unique next configuration. Or there may be, in general, because it's like a non-deterministic Turing machine, there may be several possible successor configurations. So in general, there may be up to any finite number of them. Let's say there are k possible successor configurations that the non-deterministic Turing, the probabilistic Turing machine can potentially go to in one step from this configuration. So this might be write a blank and move the head 1 to the right. We might have write a 0 and move the head 1 to the left, or write a 1 and keep the head where it is. So that would be 3 possibilities. But in general, there will be some finite number of different possibilities. And so then my execution model is, if you have k different possibilities, the machine conveniently has available a fair k-sided dice, whatever that would look like, and it selects the corresponding successor configuration. Okay, so it just makes a fair choice with either uniform probability, so 1 over k probability to go to each of the successor configurations. So often non-deterministic Turing machines are defined only allowing at most two possible successor choices, and you make a fair toss of a coin simply between 2 possibilities. So what I'm doing looks a little bit more generous, but is in fact equivalent, as that'll be, you can see, I think you'll do that in the exercise class this week. Okay, so we have in general k successor configurations from any configuration. When we have more than one, then the choice between the successor configurations is chosen with probability 1 over k. So then when we execute a probabilistic Turing machine on an input word, say we're trying to see if we accept or reject the word for some language that we're looking at. So we'll execute the probabilistic Turing machine. It'll start in the start configuration. It'll go to successor configurations where each time there's a choice, it makes a probabilistic choice with 1 over k probability for the appropriate k, which may change from configuration to configuration. Sometimes there may be 3 choices, sometimes 2. But anyway, it'll make its choices, and that'll give us a run of the Turing machine. The run of the Turing machine is going to be a sequence of configurations, each one where we get from each one to the next one in a single step of computation. And the run that we get that's probabilistically generated will either be finite and ending in a terminating configuration, or it will be infinite. Those are the 2 possibilities for the run. Okay. And notice that in the case that the run is finite, then we've made finitely many probabilistic choices to get this run. So the probability of having obtained exactly this run will be the product of for each choice where we chose between k things, the probability of having chosen the one we did will be 1 over k. And the probability of having chosen this run will be the product of all those 1 over k, where the k may vary from configuration to configuration, but it'll be the product of all those 1 over k choices. So it's going to be some finite non-zero probability, okay, that we got of getting that run. Whereas if we had an infinite run, we may have had infinitely many probabilistic choices along the way. So there may be a 0 probability of getting that run. It may have required infinite many probabilistic choices to get exactly this run. Okay. But we're going to be more interested in finite runs. So in the first case, when you have a finite run of the Turing machine, you do have a finite probability of that particular run occurring. So then for a probabilistic Turing machine, there are 2 different ways of measuring the time. Well, there are some other ways, but we're going to look at 2 different ways of measuring the time. So again, we're going to look at the time function for the Turing machine M on inputs of size n. So again, it's going to be a function from natural numbers to, well, at least to non-negative real numbers. So the worst case time is saying we want to take the time over all possible inputs W of size n, of length n, and all possible runs of the Turing machine on input W. Okay, so we're looking at the maximum computation time over any of the possible sequences of probabilistic choices on all inputs of the Turing machine of size n. So in the case of the simple Turing machine I showed at the beginning that went into a loop or either went into the accept state, irrespective of the size of the input, because it doesn't even look at the input, the worst case runtime there is infinite, because the maximum number of steps in the run there was a possible infinite sequence run. So there was an infinite sequence run, and so this actually, that Turing machine actually has an infinite worst case runtime. Now you could imagine it could be quite useful to do that sort of thing in practice, and in fact it is quite often useful to have little loops where you make some loop of probabilistic choices and exit when something happens. That's a common useful feature in computation. So it's not actually very useful to count that as taking infinite time, especially when as we saw in that case, the expected runtime in that case was only 2. And in fact, if you run that in practice, you don't have to wait very long at all. I mean, it doesn't need to halt in 2, but you're not going to wait very long for it to terminate. So this worst case runtime is not really the right notion of runtime for probabilistic computation. However, a lot of the literature on probabilistic complexity does base itself on worst case runtime. And in fact, the Aurora and Barak book, which is the main course textbook, bases all their definitions on, pretty much all the definitions on worst case runtime. It's really the wrong notion for probabilistic computation, but still a lot of textbooks base their definitions on it. So I'm going to not do that. I'm going to follow a different route and use what I think is the better approach, and use, but I think expected runtime is a better basis for the definitions. But at the end, we'll see that we're going to get an equivalent class of efficient probabilistic computation. I mean, whether or not, whichever notion of runtime we use, we're getting an efficient definition. But I think it's better and more intuitive to start with the notion of runtime that is more appropriate for probabilistic computation, and that's expected time. So the expected runtime, so I'm using X for expected runtime of the machine M on inputs of length n, is again, it's worst case in the sense that we're taking the worst of the expected runtimes for the worst input W of size n. So again, we're going to take the maximum over all input strings W of size n. We want to look, so we're saying what is the expected runtime for inputs of size n, and we want to say the expected runtime for an input of size n is at least this, is at most this, expected is at worst this function. So we maximize over all inputs of size n. This means this is expectation here. So for every input W of size n, we look at the expected number of steps in a run R of the machine M on input W, which again may be infinite in some cases. One can have Turing machines that have an expected infinite runtime, but we're wanting to bound the computation time, so we're going to hope that it's finite. And in the case that it's finite, we just find the expected time to be the maximum of the expected runtimes on inputs of size W. So inputs W of size n. And it's rather easy to show that the expected runtime is always less than or equal to the worst case runtime, because if the worst case runtime is finite, then the expected runtime is obtained by averaging lots of runtimes, of which this is the maximum one. So this average is definitely going to be less than equal to the upper bound of the things we're averaging. Okay, right. So we've got 15 more minutes for the first part. So the main two things I want to do today before introducing BPP are to show two interesting and useful probabilistic algorithms that motivate some different, in the two cases, different benefits of augmenting, that's enriching the computation model with probability. So the first one is this problem, which is, suppose we're given a sequence of n numbers, so an array, if you like, of n different numbers. And the problem is simply, given some appropriate k between 1 and n, find the kth smallest element in A1 through to AN. So we're not thinking of these numbers as ordered. It's not a sorted list. We want to find the kth smallest element in this sequence. So just hands up if you've seen algorithms to do this before. It's probably quite a common thing to do. And have you seen the randomized algorithm for it? Okay, so I'm sorry, this is going to, almost everyone's seen this then. So this is going to be repeating things you know, so we can probably go quite quickly in it. But in any case, let's treat it at an appropriate, respectful speed. So the first solution would be simply just sort these n numbers and then return once you've got a sorted list, then go through from the beginning and count to k and return the kth element in the sorted list. And so here I'm going to measure the complexity just in the size of n, which is not completely correct, because if we're really being very strict and doing it on the Turing machine, then each number will have its own length of representation, and we should really measure the complexity in the overall length of the input. But let's not be too fussy about that. So let's worry about the complexity in here, the number of elements in the list. And then if we do this algorithm that sorts the list and then returns the kth element, then, as you may know, the best algorithms for sorting a list take big O of n log n time. So this way, the sorting takes big O of n log n, then returning the kth element in the sorted list, that's O of n, because we just need to scan through the list once, not even all the way. Or if it's in an array, then we've got instant access. Anyway, the algorithm as a whole is big O of n log n. So let's instead look at a different approach, and this is the probabilistic algorithm. So we're going to find a recursive algorithm to find the kth ordered element in an unordered list of n numbers. So the way this works is so the idea is to do a sort of recursive algorithm that's going to reduce it to a smaller problem, a bit like divide and conquer, where you split something up and do the two parts separately, except in this case, we're only going to have one part to do, but we're going to reduce the size of. So what we do is we simply randomly choose some element in this list of elements. So we can do that by randomly choosing an index for it between 1 to n. So I'm sort of rather old-fashionedly indexing from 1 to n rather than from 0 to n minus 1, like one would do in a programming language. But anyway, so we'll randomly choose some index for one of these elements with the uniform distribution. And once we've done that, we can go through the elements of the list and partition it into 3. So the reason I'm partitioning into 3 is I'm allowing this list to contain repetitions here. Quite quite often one sees this algorithm explained in a way that only works if the list of numbers doesn't contain any repeated numbers. But anyway, I think it's just as nice to do it for lists that can contain repetitions. So we simply go through this list of elements, and we essentially partition it into 3 parts. For each element, we check to see whether it's strictly less than the element ai. So essentially, by choosing I, we've chosen one of these elements, a sub I. And for each element, we choose if it's strictly less than a sub I, and then we put it in the b's. If it's strictly greater than a sub I, and then we put it in the d's, or if it's equal to a sub I, and then we put it in the c's. So we're going to partition the list into 3. This part contains, so this is a permutation of the original list. This part contains all the elements. They don't need to be ordered, but they are, because we're not sorting the list. But nonetheless, in some order, it's all the elements that are strictly less than a sub I. This part contains all the elements that are equal to a sub I. So it's the right multiplicity of the number of elements that are equal to a sub I. And this part contains all the elements that are greater than a sub I. Okay, so we have here, yeah, there's a mistake there. It should be 0 is less than or equal to L, because it may be that there are no elements smaller than a sub I or no elements greater than a sub I. We know that there will be at least one element equal to a sub I, because a sub I itself is, but either of the other 2 sides might be empty. So this should be, whoops, let's make that black. This should be 0 is less than or equal to L is less than m, less than or equal to n. And this is just saying that these were all the elements less than a sub I, these are all the elements equal to a sub I, and these are all the elements greater than a sub ai. And then once we've done this, well, we can see where we made the partitions. And if k, if the number k, we're looking for the kth smallest element in the list. If the number k lands in this part, if we count 1, 2, 3 up to k, here, if it lands in the C part, then we know the kth smallest element is equal to a sub I. So we can return the value of a sub I. If k is less than or equal to L, well, then we can reduce it to the smaller problem of finding we can now make a recursive call to a smaller list. The list of the B things contains at least one element less than the original list. So we want to find the kth element in this list of B things. And if k is greater than m, then what we want to find is then we know that the kth element is in the D's. And what we want to find is the k minus m smallest element in the D's, okay? So that's how we split it into a recursive, algorithm. So let's look at the runtime of this algorithm. And in fact, one can see that the worst case runtime of this algorithm is big O of n squared, where n is the number of elements in the list. So here we're doing worse than sorting the list and then finding the kth element in the sorted list. That was big O of n log n. So the worst case of this runtime is big O of n squared. But nonetheless, this is actually the efficient algorithm that one uses in practice for this problem. It's the sort of the best algorithm for this problem. So that worst case runtime is not really relevant. So it turns out that the behavior of this algorithm in practice is best explained by its expected runtime. And the expected runtime is big O of n. So let's prove that the expected runtime for this algorithm is big O of n. So to prove that, I'm actually going to assume that we are sorting, not sorting, but finding the kth element in a list of elements that are all distinct. I said this algorithm works also if the elements are not distinct. But for to analyze the runtime, I'm going to assume that they are distinct. And actually, that's no loss, because when the elements are distinct, the collection of C's here always has exactly one element. When they're not distinct, the collection of C's may have more than one element. And the more C's we have, the faster the algorithm goes, because if we've got more C's, then we've got smaller lists of B's and D's to look through. So actually, to restrict to lists in which all the elements are distinct is not only makes the runtime worse, not better. And we're going to, in any case, show that the algorithm has a linear upper bound. So in the case that all the elements are distinct, then when we partition like this, we always have exactly one C, which is the element A sub I itself. So that means that M equals L plus 1, and also that the element A sub I, so Cm is the element A sub I. The element A sub I is then the mth smallest element in the list, because A sub I will be here in this position Cm. They're exactly m minus 1 elements strictly smaller than it, and n minus m elements strictly bigger than it. So A sub I will be the mth smallest element in the list. So that's hopefully what it says here. So the order rank of AI in A1 to AN is m, which equals L plus 1. So we want to see what the expected runtime is. So for the expected runtime, well, the idea is we're going to have some constant C, which we can use to absorb all the computation we do in the non-recursive part of the algorithm. So in the non-recursive part of the algorithm, when we start the algorithm, the non-recursive part is randomly choosing an I. That doesn't take any time at all. Well, it takes one step, let's say. Then going through A1 to AN and checking each element to see if it's smaller than, equal to, or greater than A sub I, and putting it in the right place as appropriate. So hopefully you can believe me that that takes big O of n time. That's sort of linear. We just need to go through the list of elements A1 to AN and do the appropriate thing with each element. We can put these on 3 different tapes if we want to. But if one's doing this in practice in an array, there's a nice way of doing this that permutes the array in place, related to what's called the pivot algorithm in quicksort, for those of you who've done that sort of thing. So the point is the non-recursive part of the algorithm is big O of n, and then we go to the recursive calls. So if it's big O, the non-recursive part is big O of n, we have some constant C such that we can bound the non-recursive part of the algorithm, the runtime, by C times n for that constant C. So then T1 will simply be C. We've got one thing, then that's going to absorb everything we need for T1. And Tn will be C times n, at most C times n for the non-recursive part of the runtime. And then we want the expected time of the recursive call. We're adding it, we added the expected time of the recursive call. So the expected time of the recursive call is, so maybe I'll go to here. I'm going to just draw a very simple little picture. Whoops. It's not very well drawn, but anyway. So suppose we're sorting a 5, not sorting, but trying to find the, so suppose n equals 5 and k is 3. So we're trying to find the middle element in a list of 5 elements. So then we start by randomly choosing an index between 1 and 5. That's the I. And that will pick out an element a sub I, which when we've partitioned our list, oh, I need to go back to here, which when we've partitioned our list of elements into the B's, C's, and D's, that a sub I will be in position C sub M. That will be C sub M. So M will be So I'm going to call this M here. And the point is 1, 2, 3, 4, 5. So if AI is the smallest element of the list, then M will be 1. Okay, if AI is the smallest element of the list, then, so if we randomly pick the smallest element of the list, then when we partition B's, C's, and D's, we don't have any B's, we just have AI here, and then we've got 4 elements above it. And so we end up sorting a 4-element, sorry, not sorting, but we end up doing the recursive call to a 4-element list. So in this case, we end up doing a recursive call to a 4-element list, if we like. So whereas we started with 5 elements, we then do a recursive call to 2 elements. If our AI was the second smallest element, then we've got 1 element that's in the B's, AI in the C's, and we end up looking for the smallest element in the 3-element list. If AI is 3, if the third element, well, then we found the element we want, so we just return, so we don't do any work. If it's 4, if we had if AI was the 4th smallest element, then we end up then we've got AI, we've got the element above it, and we end up looking for the 3rd smallest element in the B's, which has length 3. And if AI is the sorry, yeah, that's right. And if AI is the largest element of the list, then we don't have anything in the D's. The C is AI, and we end up looking then for the 3rd smallest element in a list of length 4. So somehow the recursive picture is like that. I hope that made sense. And because there's a probability 1 over n, so 1 over 5 in that picture for picking any of the elements, in the case that M is strictly smaller than K, we end up doing a recursive call to n minus M. And in the case that M is strictly greater than K, we end up doing a recursive call to M minus 1. So here we see if M was less than K of 3, we're doing a recursive call to n minus M, so n minus 1 here, so 5 minus 1 here, 5 minus 2 here. And here, when it's greater than K, we end up doing a recursive call to n minus 1, so 4 minus 1 here and 5 minus 1 here. And there was a 1 over n chance of any one of those happening. So for the expected runtime, we have this equation here. And given this, it's very easy now to prove by induction on n that Tn is less than or equal to 4 times C times n. So we simply copy this inequality here. So Tn is, so the non-recursive part of the algorithm plus 1 over n times the sum of the Tn minus m's and the sum of the Tn minus 1's. And by the induction hypothesis, we can put in, the induction hypothesis is that So n minus m and n minus 1, these are all smaller numbers than t of n. So by induction hypothesis, we can use that that t of n minus m is less than or equal to 4 times c times n minus m, and t of n minus 1 is less than or equal to 4 times c times n minus 1. So then we can pull the 4 times c out, and we get cn plus 4c over n times the sum from 1 to k minus 1 of n minus m plus the sum from k plus 1 of n to m minus 1. So now, if you want to, you can expand out these sums using your formulas for summing the elements of an arithmetic series. And it's not difficult to, well, this is just the sum, this is just the formula for the sum of the first k minus 1. Oh no, so it's not quite. Well, anyway, for summing an arithmetic series, these formulas, you can plug them in and do a lot of calculation. Well, not that much, but anyway, do some calculation. But anyway, let me just tell you that this value here is less than or equal to 3/4 n squared. And when we plug in, so this is less than or equal to 3/4 n squared. When we plug that in, it all cancels and we get 4cn. So indeed, by induction, we've proved the inequality we want to prove. And just to say, this inequality here, the sum from m equals 1 to k minus 1 of n minus m plus the sum of m equals k plus 1 to n minus 1, it's actually very easy to see that this is less than or equal to 3/4 n squared, because you'll recognize this picture as the one I already drew. It's got a bit more detail. I mean, here we've got n equals 7, and I'm going to put k equals 4. If we add up the n minus m's on the left here, I've colored them in green. And if we add up the n minus 1's on the right here, I've colored them in green. And we can see that the green, if we partition the square like this with the orange line, vertical line, and the diagonal line, the green stuff all fits in this area, and the green stuff here all fits in this area. So the sum of these values is less than, if we take the area of this, is less than or equal to the yellow part in this square. And this part, we've got a diagonal here, and well, k is a vertical line that we put somewhere down. And if you look at wherever you put k, if you color it in yellow like this, the maximum value you can get is 3/4 of the area of the square. But that's when k is in the middle, then you cover exactly 3/4 of the element of the area of the square. If k is at the edge, you cover half the area of the square. So the maximum value of this is 3/4 n squared, and the green part is certainly smaller than the yellow part. So that's a nice proof of that inequality. And with the proof of that inequality, we've seen that this randomized algorithm we have indeed, in terms of expected time, improved on the non-randomized algorithm. Okay, sorry for overrunning. We're going to have a 5-minute break now till 1/4 and then we'll have 35 minutes for the second part, and then a 10-minute break before the presentations. Let me just pause the recording. Okay, so this nice simple algorithm for finding the kth smallest element in a list of elements is one simple example of a useful probabilistic algorithm, one that's really useful in practice. And probability is needed there because the whole algorithm is based on dividing the list into these 3 parts. And okay, well, rather than randomly choosing an element, we could deterministically choose an element to partition the list by. But the problem is, how do we deterministically choose an element? Without knowing something about how the elements lie in order with respect to each other, how do we decide to deterministically choose one of the elements rather than another? It's actually very difficult to make that sort of analysis. And it's much easier just to choose a random element and say, and sometimes we'll choose a bad random element like this, the largest element or the smallest element, and we won't partition the list, but split the list very much. But on average, if we choose random elements and we've got a big list, we're going to split the list well enough that we're going to, that it really does affect it really does give a reasonable runtime. And the analysis bears that out, the mathematical analysis, because the mathematical analysis says we've got expected linear runtime. So jolly good. So that's a nice simple algorithm. It's very easy to write the algorithm that works. A more sophisticated algorithm is well, the family of algorithms are probabilistic algorithms for testing whether a number is a prime number. So this is a large number is a prime number. This is called primality testing. So just let's do a hands up again. Hands up if you have seen randomized algorithms for prime testing in other courses. Yeah. You have, yeah. Well, there are a number of them. You might not have seen this one, but we'll see. Exactly this one, the Miller-Rabin one, because there's also the Solovay-Strassen one. Okay, but in any case, well, it's nice to see it again. It's a beautiful algorithm. So testing whether a number is a prime number is, you've got a large number. Well, the length of the number is kind of the logarithm of the number, so to speak. But you can't simply go and test all odd numbers up to the square root of n to see whether they divide the number, because that would be exponential in the length of the input. That would be a lot of work. So that's if you've got a very large number, that's not going to efficiently be able to tell whether it's prime. So it's nice to find other good tricks to tell whether a number is prime. And one of the nicest algorithms that's actually used in practice is based on a small modification of a very simple theorem of number theory called Fermat's little theorem. Now, Fermat's little theorem is about arithmetic modulo a prime. So modulo arithmetic, or if you like, arithmetic in the field Z sub P, where P is a prime number. So that's integers modulo P. So if P is a prime, then it's actually more generally for any number A that does not divide by P. But anyway, let's just restrict the range 1 up to P minus 1. If we take A to the power of P minus 1 and calculate that modulo P, we always get 1. So A to the P minus 1 minus 1. So A to the P minus 1 all minus 1 is a number divisible by P, essentially. So I'm not going to prove this. It's not very difficult to prove. Essentially, you can prove it if you know that the integers modulo P form a field, and therefore you have a multiplicative, the numbers from 1 to P minus 1 under multiplication are a commutative group. And given that, if you consider the orbit of A, of the powers of A under that, so it's not really the orbit, but if you consider the subset of powers of A under the under multiplication, then that forms a subgroup, and therefore it has by the standard theorem in group theory, it has an order that divides the order of the group, and this follows. So actually, I said I wasn't going to prove it, but I've basically outlined the proof. Anyway, that's a lovely little result in number theory, much easier to prove than Fermat's last theorem. So this can almost be adapted directly to a test for primality, which I could outline how to do that, but one gets a flawed test, flawed F-L-A-W-E-D, so with a flaw in it, with an error in it. One gets a problematic test doesn't quite work just adapting this little theorem directly. So in the 1970s, Miller and Rabin, between the two of them, Miller in 76, I think, and Rabin finishing it off in 1980s, realized that there was one could adapt this to a more subtle test, a more subtle property of primes, which can be used as the basis as an algorithm for testing a number to see if it's a prime. And this more subtle property is that if we have a prime number, we're only interested in, if we're testing a number as prime, it's enough to, we're interested in large numbers, so it's enough to restrict to odd numbers because the only even prime is 2. So if we got a large number and it's even, we know it's not prime, so it's enough to restrict to odd numbers. So we'll just look at odd primes. So if you have an odd prime, well, any odd number you can write uniquely as in this form, 2 to the power of s times d plus 1, where d is odd. Because if you've got an odd number, subtract 1 from it and you get an even number. Then divide by, so you get an even number when you subtract 1 from it. Divide by 2 as many times as you can. And the number of times you can divide by 2, well, that's s minus 1. Hang on, no, that's s, the number of times you can divide by 2. And when you eventually get an odd number, that's d. Yeah. Anyway, so if you've got an odd prime, split it like this. So s is at least 1. D is odd. We can compute that efficiently from P because subtracting 1, that's a linear time operation on the representation of P. Once you've got that, well, the number of times you can divide by 2, if you're in binary representation, you just see how many zeros there are at the end of the number, take off all those zeros, and then you're left with D. It's the remaining, so count the number of zeros, that gives you S, and then the remaining block of stuff to the left of the zeros, that gives you D. So it's very easy to do this once you've subtracted 1 from the number. Then splitting it like this, then for every A smaller than P, one of the following holds. So we now, instead of taking A to the P minus 1, we take A to the D. So either A to the D is congruent to 1 modulo P, or for some multiple 2 to the power of r times d. So this includes a to the d in the case that r equals 0, a to the 2 times d in the case that r equals 1. So for some r between 0 and s minus 1, if p is a prime number, then a to the power of 2 to the r times d is congruent to minus 1 modulo p. One of these holds. So this is what Miller essentially observed. And it's actually easy to prove this from Fermat's little theorem. So let's prove this property. So suppose P is of the form 2 to the power of s times d plus 1, and it's a prime number. So by Fermat's little theorem, a to the power of p minus 1 is congruent to 1 modulo p. So that's a to the power of 2 to the s times d is congruent to 1 modulo p. But a to the power of 2 to the s times d, well, that's the same as a to the power of d squared, and so on, and squared s many times, where we do that squaring s many times. So by Fermat's little theorem, if we take a to the d and square it, we get 1 modulo p. But that means if we take the square root of this number, if we take any number that equals this squared, it'll be some, if we take, so we've got this number here. If we take one of the squareds off, we'll have some number modulo p whose square is 1. But because integers modulo p are a field, the only square roots of 1 are 1 and minus 1 modulo p. So if we take one of these 2's off, we get -1, where we either get 1 or -1. And if we get 1, if we take another 2 off, we either get 1 or -1. And if we take another 2 off, we get 1 or -1, and so on. And while we stay at 1, eventually we'll get down to a -1. So when we get right down to the bottom, a to the power of d is either 1, or somewhere along the line we went into a -1. Okay, so that's the proof that one of these will hold. So either we're 1 all the way down, in which a to the power of d is 1, or somewhere along the way, if we go away from 1, we must go to the other square root of 1, which is -1. So the one of these r's will have a to the 2 to the power of r. D is congruent to -1. Okay, so that's a slightly more subtle property that holds prime numbers than Fermat's little theorem. But why this property is good is that the main thing that Miller and Rabin between them proved, I think this part was more Rabin, this exact result, is that there's a Miller-Rabin property also for composite numbers. So if you have a composite number, so this is supposed to be restricted to odd numbers. I don't know. So if we have an odd number, composite number, so again, we can write, if it's an odd number, we take 1 away from it, and then again, we've got an even number, so we'll have 2 to the power of s, where s is at least 1, times d, where d is an odd number. So I should clarify here, d is supposed to be greater than or equal to 1, and sorry, s is greater than or equal to 1, and d is odd. So again, any odd number splits uniquely into this form, and again, we can compute it efficiently. Then we can still consider the property. This will not hold for every a from 1 to n-1. We crucially used the fact that p was prime before to show that it holds for every a in the case that p is prime. But if it's a composite number, we can still consider the property for an a of when it satisfies one of those two properties, that either a to the d is congruent to 1 modulo n, or for some r between 0 and strictly smaller than s, a to the 2 to the power of r times d is congruent to -1 modulo n. So we can still consider that property. We knew if n was a prime number, one of these would hold for every a. If n is a composite number, well, what Miller and Rabin proved is that actually one of these properties, there are only of the n-1 numbers between 1 and n-1, at most n over 4 of them satisfy one of these properties. Okay, that's a very curious result. This is no longer a very elementary result. This requires a bit of mathematical sophistication to prove it. Miller actually didn't use this at all. He didn't use exactly this. Miller instead assumed the generalized Riemann hypothesis was true and used the assumption of the truth of the generalized Riemann hypothesis to get some information on the distribution of the numbers a that satisfy one of these two properties. So he did some very sophisticated stuff. So Rabin realized that actually one could actually make things simpler by counting simply the number of a's that satisfy one of these properties and showing there are at most n over 4 of them. So this is not simple number theory, but the point is we've got these two properties. For any odd number, we can check whether for any odd number and for any a between 1 and n-1, we can check whether these properties hold. I should say it's possible to check these quite efficiently using nice efficient algorithms for taking powers modulo n. So for any number, we can efficiently check if these properties hold. And we know that if the number n is prime, these properties always hold. And if the number n is not prime, one of these properties holds for at most a quarter of these numbers. So given this, we can get the Miller-Rabin primality test, this algorithm. And the idea is this is going to test if a large odd number is a prime number. So the input is an odd number, n. And the algorithm is first calculate the s and the d. So subtract 1 from n, count the number of zeros at the end of it. D is the remaining block of digits. That's an odd number ending in 1. Then, and this is where randomness is used crucially, randomly choose some number between 1 and n minus 1. So we're going to choose that number with the uniform distribution. And we check to see if one of the following holds. So if we choose 1, it will always hold actually, because you'll always get this a to the d is equivalent to 1 modulo n. But we check to see if one of these test properties holds. So either a to the d is equivalent to 1 modulo n, or for some r between 0 and s minus 1, a to the 2 to the r times d is equivalent to minus 1 modulo n. And if one of these two properties holds, then, well, if n were a prime number, we're guaranteed that one of these properties holds. That was the Miller-Rabin property for prime numbers. So if one of the properties holds, we say, well, the number is possibly a prime number. And if neither of these properties hold, then we know the number is composite. Because if it were a prime number, one of these properties would certainly hold. So if neither of the properties holds, we return composite. The reason we say possibly prime here is because there's a chance, if n is a composite number, there is a chance that nonetheless we will pick one of the, at most, 1/4 of these values, but we'll pick one of these values for which one of these properties does hold. So for up to a quarter of these values, when n is a composite number, one of these properties does hold. So if one of these properties hold, we don't know for certain that the number is a prime, but if neither of the properties holds, we do know for certain that the number is composite. So what we can say precisely about this algorithm is that by these Miller-Rabin properties, the property for composite numbers and the property for prime numbers, that if we give the algorithm a prime number as input, then the algorithm will certainly return possibly prime. Because whatever a it picks, one of a and b, little a and little b will hold whatever number a it picks. If we give n a composite number as input, well, then it randomly picks, the algorithm randomly picks a value a. And if it picks one of these at most n minus 1 over 4 values for which the test properties hold, it will return possibly prime. And if it picks any of the other values, then it will return composite. And because there are at most n minus 1 over 4 values that for which one of the properties little a and little b hold, if n is a composite number, the algorithm will return possibly prime with probability at most 1/4. And it will return composite with probability at least 3/4. Okay, so we've got an algorithm that if it tells us possibly prime, we don't actually know that it's right. If it tells us composite, we know that the algorithm is telling us the truth and we don't have a prime number. But the beauty of this algorithm, well, the probability of 1/4 of an error looks, that's quite a high probability of an error. We're not going to want to base any sort of critical software that relies on our number being a prime on the probability of 1/4 of an error. But the beauty of this algorithm is that it's easy to reduce the error to any desired threshold by running the algorithm many times. So for example, suppose you want to test a large number n is prime with only a 2 to the power of minus 50, 1 over 2 to the power of 50. That's an extremely, extremely, extremely small probability of making an error. Well, we've got a 1/4 probability of an error from one run of the algorithm. If we run the algorithm 25 times, then we've got a 1. Then for the algorithm to be wrong, it would have to be wrong on all 25 of those runs. So the probability of that happening is 1/4 to the power of 25, or 1/2 to the power of 50. It's at most 1/2 to the power of 50. So we simply, and that's not running something 25 times is no big deal. It's an efficient algorithm. We can run it 25 times. So we run the test 25 times on n. If n is prime, then we see, if n is prime, we certainly see possibly prime 25 times. If n is composite, then with probability at least 1 minus 2 to the power of minus 50, which is very, very, very close to 1, we see composite at least once. And people often use 1/2 to the power of 50 as the probability of an error here, because it's such a small probability that physicists reckon that there is more than a 1/2 to the power of 50 probability of a cosmic ray zapping your computer and giving you an erroneous result by flipping the output bit in your computer's memory. So you know, this is as certain as you can be that your number is indeed a prime number. So it's a beautifully simple idea. And the other beauty of the algorithm is, well, how essential randomness is to this, because so the difference between Miller's version of the algorithm and Rabin's version of the algorithm was Miller had a deterministic test. Rather than randomly picking this value A, Miller deterministically chose an A. But in order to do so, he needed to know how the A's that satisfy how the values A that satisfy one of these two properties are distributed amongst the numbers 1 to n-1. And in order to get any information about that, he used the generalized Riemann hypothesis. So an unsolved question in mathematics. But randomness just gets around that beautifully. We don't need to know how they're distributed. We just need to know how many values there are. Because if we pick a random one, it's oblivious to the distribution of the values. So it's a beautiful solution. That was the randomness part was Rabin's idea here, although building on an earlier algorithm of Solovay and Strassen. So if you would like to see another such algorithm, there's the Solovay-Strassen algorithm, which is in the Aurora Barak textbook. Okay, so we've seen two now nice probabilistic algorithms. So from that, we can see some general considerations on probabilistic computation. So firstly, what's the point of randomization in the first place? Well, we can make in both algorithms, and essentially the main use for it is to make choices that we don't know how to efficiently determinize. When trying to find the kth smallest element in a list, we didn't know how to pick an element to partition the list, so we randomly choose one. That works very efficiently. When checking a number is prime, we don't know how to choose these test values, little a, that we were using, so we randomly select one, and again that works very effectively. So it's a beautiful idea that we don't know how to determinize a choice, but we can is often useful to be able to randomly choose one. We've seen that the expected running time, we have a different notion of running time for randomized algorithm. It's the expected running time that's relevant. And considering the expected running time allows us to improve the runtime compared with the worst case time of a non-deterministic algorithm. And we've also seen in the primality testing that some error can be tolerated as long as we can manage the probabilities of the error. So as long as we can keep those probabilities under control, we know what the probabilities are, we can allow some error to creep into our algorithms, and that gives us a very useful algorithmic way of writing powerful algorithms, if we can make mistakes but keep the error of making a mistake under control. So taking all these lessons together, what we want to do now, what I want to do now is modify the definition of the probabilistic class of problems, so the class P of probabilistic time algorithms, to be what is intuitively the right notion of efficient, meaning probabilistically time-bounded algorithm. Of polynomially time-bounded algorithm for probabilistic computation. So to do this, we're going to incorporate expected time and the possibility of making an error in a bounded way. So we first say a probabilistic Turing machine runs in, and now the definitions are exactly as one is the expected definition of expected polynomial time. A probabilistic Turing machine runs an expected polynomial time if there is some polynomial P on the natural numbers that gives an upper bound to the expected runtime of the algorithm in the size of the input. Okay, so no surprise at all. We've got the definition of expected time on the earlier slide. So that way we're incorporating expected time. The other thing I want to do is incorporate allowing the Turing machine to make an error. Now, the primality algorithm only made an error in one direction. If it returns composite, it's all we know the number's composite. If it returns possibly prime, we're not sure if the numbers are prime, so we then need to control the error probability. But actually, in general, you can imagine that in some cases it might be useful to allow the probability of error to occur on both sides. So we want to know accept or reject, but there might be some, as long as we can keep the probability of error on the accept side small enough and the probability of error on the reject side small enough, that should be good enough. So we want to give ourselves the most liberal notion, the most inclusive notion of efficient probabilistic computation. So to the appropriate definition then is, we want to talk about a probabilistic Turing machine deciding a language, but where it can make errors in its decision process. It might say accept or reject, but in both cases there might be an error. So we say it decides L with bounded error if, firstly, on any input, the Turing machine halts with probability 1, either in an accept or a reject state. And then we require that if we run it on a word in a language, then the probability that the Turing machine accepts is close enough to 1. And we can do this by, in this definition here, we can use any constant strictly greater than a half for this. So we have, but typically one uses 2/3 because if we're going to use two different, well, typically one uses 2/3. I don't know why, but anyway, it doesn't matter. It could be any constant greater than a half, and that will be in the exercise classes to prove that. So the point is, if you run it on a word in a language, then the probability of accepting is high. And if you run it on a word not in a language, then the probability of rejecting is high. Okay, so depending on whether you run it on a word in the language or not in the language, then there's a high probability that the Turing machine will do the right. Whatever kind of word you run it in, there's a high probability that the Turing machine will do the right thing. And again, you might say 2/3 is not very high, but there's a slightly more complicated way of running. You can again run the algorithm many times and make the error any value you want, although the analysis in this case is a little bit more complicated, but I'm going to leave that for the exercise class. Anyway, the definition, I think, is now quite intuitive. So we've got this notion of running an expected polynomial time and deciding a language with bounded error. And the BPP, bounded probabilistic polynomial complexity class, is simply the class consisting of those languages, those problems, such that there exists an expected polynomial time probabilistic Turing machine that decides the language with bounded error. So exactly what we would expect given the previous definitions. Okay, so that's really the material I wanted to cover today. I just want to make a couple of remarks about this. So the definition I've given is not the standard one. So in the textbook, but also on the Wikipedia article, if you look at the definition of BPP, it uses worst case time rather than expected time. This is in fact equivalent, and that's going to be something that you'll do in the exercise class in this case. So I prefer to give the definition in terms of expected time because it gives a more liberal class. It's a priori a more liberal class. It allows more algorithms to include, and those algorithms include algorithms that one really uses in practice and considers as efficient algorithms, such as this algorithm. Well, sorry, I was going to say such as this algorithm for finding the kth element in a list. Actually, that runs in worst case polynomial time anyway, because the worst case is big O of n squared. But the point is that the expected time is the time that makes sense probabilistically, it's the realistic time probabilistically. So it's natural to incorporate that in the definition. And just a comment on the relationship to other complexity classes. So it's easy to see that the class P is contained in BPP because a deterministic algorithm is a fortiori a probabilistic algorithm. There's just no probability involved. But where PPP is in relation to other classes is a bit tricky. So in the exercise class last week or the week before, you did the polynomial hierarchy or some parts of it. So in fact, BPP is contained in the intersection of the sigma 2 and the pi 2 classes in the polynomial hierarchy. But this intersection is really quite a tricky property. So it took a few years for people to establish this. It's much easier to see that BPP is contained in P space. I might put that in the exercise class as well. I'm not sure. But anyway, it's good to know it's contained in this intersection in the polynomial hierarchy. It's not known if BPP is contained in NP or co-NP. So the relationship between BPP and NP and co-NP is not known. But people aren't too concerned about that because actually people widely believe that BPP is equal to P. And the intuition here is BPP, in order to run the algorithms, we're using random choices. And if we have a sufficiently good deterministic random number generator, a pseudo-random number generator, then perhaps we can do this deterministically using our deterministic pseudo-random number generator. And there's a whole field of complexity theory about the properties of random number generators, and people believe something called a strong pseudo-random generator exists. And if it does, then actually one can prove that P equals BPP. So actually, anything one could do in probabilistic time, people believe it can be done in probabilistic polynomial time, people believe one can do it deterministically, but basically by simulating the probabilistic algorithm using pseudo-random number generators. Okay, I've slightly overrun, but only slightly. I think, well, because of that, we'll aim to start at 2 minutes past 10 for the presentations. Okay, so that's everything for the video, so I shall stop the recording.